All right, well, welcome back. Um, this course, Greenhouse Technical, is, I think, a fun course. We get to learn some of the equipment side of the greenhouse. Um, definitely, there is a lot of equipment in the greenhouse, and so the idea is to introduce you to some of it. It's not going to turn you into an expert, but that will happen over a few years of actually working in a greenhouse. So, um, we'll start the course by talking about heating systems. You may have had a bit of an introduction at one point in your courses with greenhouse construction, but let's dig into this a little bit because heating systems are varied and either simple or quite complicated. So I want to give you an overview in this lesson, and then subsequently we'll go into a bit more about operating uh, strategies, and that will dovetail with what Matt's teaching you in greenhouse controls. So there will be a little bit of overlap here and there between these courses, but the idea is to sort of have a consistent narrative to send you on your way. Makes sense, right? So no one course is going to stand alone. They kind of work together. Um, I already said too much there, but anyways, you'll figure it out. Uh, I'm not sure what I was thinking when I made the slide. I think I just found this one particular picture entertaining. I don't know, but this is a typical heating section in a greenhouse. A lot of pipes going everywhere, and when you're back on campus, I'm going to walk you through the boiler room in our greenhouse, and hopefully, the next time you see something like this, it won't be quite so shocking. You'll understand what you're looking at. Anyways, so as far as heating goes, heating is a substantial cost to greenhouses. Right here, I've got around 35% of total operating costs. So your labor cost in a greenhouse is usually around 35 to 40% of your operating costs. So we're way up there, second highest cost on your ledger. But the biggest thing is that it's the most unpredictable, right? Um, crops, you know roughly what the pot and the soil and the cuttings cost. You know how much labor it takes to plant it and maintain it. Those are fairly consistent. They may ebb and flow a small percentage each year, but when it comes to labor, first of all, we don't even know if it's going to be a cold winter or a warm winter. We don't know if there's going to be a lot of snow or a little snow. And we don't know about the price of the fuel. Will it change, right? I mean, you go to the gas station, your gas price changes from day to day. So the same happens in the greenhouse world. I mean, predominantly we use natural gas, and in the 15 years that I ran our greenhouse, we had the price of gas went from uh, the highest cost of 52 cents per cubic meter to the lowest being 14 cents per cubic meter. That's like a five-fold, four-fold increase. Um, that's crazy. That's a huge variable. And when you're dealing with a cost like that's tens of thousands of dollars in difference that you don't know if you're going to have to pay. So a lot of times we sign multi-year contracts to have more predictable pricing, but within those contracts, there's usually some variability. Um, of course, depending where you are on the planet makes a difference. The closer you are to the North or South Pole, obviously the colder it's going to get. The type of crop you grow plays a role. Like if you're a nursery and you're growing hardy plants, you don't have to keep the plants as warm. In fact, you should have a cold period. Um, then there's the type of fuel, or in many cases, the ability to switch fuels, right? Do you have alternate sources of heat? And then I did actually forget the first one, which is microclimates. That's something that we benefited in Niagara. You would have learned that in Plant Science 1, hopefully, where we have proximity to Lake Ontario. Even right now, the lake isn't frozen, which means it's never below zero. It's maybe down to around 1 or 2 degrees Celsius. So if it's minus 10 in the air, the lake's going to warm that air. So the closer you are to the lake, the warmer it's going to be. So that's that sort of buffering. Plus, we have the escarpment, which traps that warm air. So that's why we can grow fruit in the Niagara area below the escarpment. You can't above the escarpment, but below, because that warm air is trapped from the lake. and that prevents really cold temperatures from damaging stems and roots of the fruit trees. And of course, for greenhouses, that means that we have warmer climate and reduced heat needs. Lots of different fuels that are available. Natural gas is by far the most abundant in greenhouses. In northern Ontario, you start to see things like heating oil or propane, which technically is part of natural gas. Natural gas is a mixture of methane, propane, and ethane, and it's mostly methane. But it's a mixture, and that mixture actually changes depending on where you are in the country and who's supplying the natural gas, because the gas that comes out of the ground is different blends, and those different blends have different heat potentials. So that's another interesting thing to consider. Where propane is refined in natural gas, so all you get is propane, not the methane and ethane. So propane is more expensive, obviously, because it's gone through another step to purify it. But you get a consistent heat grade out of it, and so that's why it's sold for, barbecues and stuff like that. Less common is bunker oil, which is typically used in ships. So if you've ever watched the ships go through the canal here in St. Catharines, you'll see that they have a lovely plume of black smoke coming out the top of their chimney. This is nasty stuff. I don't think greenhouses really use this anymore. There's maybe a couple of greenhouses that have it as backup heat. It is definitely cheap, but it's a major headache because at room temperature, bunker oil is like the consistency of margarine. Well, maybe at around below 10 degrees Celsius. It's like margarine. So you have to warm it to keep it fluid. And what often happens is something breaks and the oil gels and it plugs all the lines on the boilers, and then it stops firing. You have to get with a torch and warm all the lines to get it to become liquid again. And it's just dirty, nasty stuff. Biomass, it is something I delved into, but the cost to run wood is somewhere around what it costs to heat with natural gas right now. So it really, if you already have the system, it's fine. But if you don't, it's not worth it. Gas will go up again. I think when we put our wood heat system in, gas was about 48 cents a cubic meter. And of course now it's like 14. So, it made sense then, but it wouldn't make much sense now. Electric heat is crazy. You don't see it very often because it's flipping expensive. I don't know. Maybe if you're using an outdoor heat pump and you lived in a really moderate climate, then maybe it would work. But I don't know. Geothermal, very expensive to install. That's where you're getting heat out of the air, out of the ground, or out of groundwater by using like a refrigerator type system in reverse. Those are expensive to make, and you require a huge area to get enough heat to heat a greenhouse of a certain size. So it's very specialized. I'm not going to say it doesn't happen, but very specialized. Thermal storage, we'll talk about that towards the end of the lesson. Maybe it's easier just to show you what that is than to talk about it now. Coal, I don't know of anyone who heats with coal. They did years ago in the UK and parts of Pennsylvania, but no one does anymore. Industrial process waste, this is really, waste heat, this is really interesting. There was a tomato greenhouse built up near the Bruce Nuclear Power Plant. It's still there. It's actually now growing cannabis. It's known as 7 Acres outside Kincardine. And what happens with this farm, when it was originally built, they have to cool the nuclear plant. And so water goes through a heat exchanger. So it's not like radioactive water, but there's waste heat. And they're just dumping it into Lake Huron at the time. And these investors came along and said, hey, what if we take the waste heat and we heat our greenhouse? And they did that for many years, but the tomato greenhouse went bankrupt. I think they don't have the proximity to markets. Like, they're way up there in the middle of nowhere. Beautiful place. And if you want to work in cannabis, by the way, 7 Acres is a fantastic farm. They do a really good job. And they treat their employees fairly well. Another one that I've seen is landfill gas, and ironically, the Walker Industries just up the road from our campus has a landfill. And years ago, they proposed to run a pipeline down to the college greenhouse to heat our greenhouse with their off gas. Because currently they have to sort of collect it and burn it so it doesn't go into the atmosphere. Because methane gas in the atmosphere is a very strong greenhouse gas because it's a large molecule that has a lot of stored energy in it, so it will heat the air. So they just have to flame it off, and it seems like such a waste to do that. Um, there's other opportunities. I look at the off gassing at in Hamilton, downtown Hamilton, where when they recycle metal, they melt it, and if you throw your stuff in the recycling bin, it's got plastic on it and paint, and there's different bits here. It's not perfect metal every time, right? There's packaging, and so what they do is they put it in a smelter, and all the stuff that's not metal burns off, and in the heat it kind of gasifies, and so it doesn't necessarily burn, it turns into a gas, and they have to ignite that gas before it exits into the atmosphere, so they have these big flames to burn it off. And it seems to me like that's something that, okay, fine, we should recycle, that's a good thing, but this burning all the gases coming off the process seems like a waste. Why not heat water and then grow something useful like food? Um, but maybe people don't want to eat tomatoes that have been grown in downtown Hamilton. I don't know. But you know, hey, I don't know. Uh, there's definitely a huge future in the greenhouse industry when it comes to climate change and energy efficiency and using technology to produce food for us sustainably, or at least more efficiently. And this is a link in your PowerPoint, not the video, but in the PowerPoint you can click on it, and it'll take you to Whole Foods and Gotham Greens. And what they're doing here is they build greenhouses on top of their grocery store, and they grow lettuce and tomatoes and cucumbers and peppers and herbs and green beans, and they sell them in the grocery store directly below. And this was the very first greenhouse they built in Brooklyn, and they have since built several more across North America. And I think it's a fantastic idea. And also, their parking lot has all these roofs where people park their cars under. There's many more of these. And what's cool about them is that they collect rainwater, which goes into a cistern to irrigate the crops. And these are all covered in solar panels. And so the entire parking lot is generating electricity to offset the electrical needs of the greenhouse. And they're using rainwater. Uh, it's just a fantastic idea. Talk about as local as it gets. Um, I think I had one student over the years that went and worked for these guys. I have lost track of them. I don't know where they are. There's also Lufa in Montreal that does this sort of thing. Um, I haven't gone on that Montreal trip, so I haven't seen it, but I know Bill McDonald went, and they definitely could use a couple of our graduates because I don't think they really know how to grow. um, so before I get into heating, I want to talk about efficiency because that's important. So what is efficiency? So that means we're talking about how much heat we get from our fuel. Um, every different, all that long list of fuels I gave you, each fuel has a potential heat energy in it, right? So if you perfectly combusted it and got all the potential heat or chemical heat out of it, you would get, X amount of heat. But of course, like everything, we never achieve perfect combustion, so we never get that perfect amount of heat extraction from the fuel. So we have to look at the efficiency, sort of a ratio of that. So typically heat is measured in BTU, which is British thermal units, and in Europe they use kilowatts. So sometimes you see kilowatts, but typically we see BTUs. When boilers get really big, they switch from BTUs to horsepower, but we're not going to worry about that right now. Um, so the BTU is a unit of heat. So let's say you've got, this amount of heat, and when it's burned at 100% efficiency. So in reality, we get less. So what we talk about is we say our input BTU divided by our output BTU times 100% gives us our efficiency. So in this case, down here, my example, let's say our furnace is producing 80,000 BTUs of heat and it's consuming 100,000 BTUs of natural gas. In other words, the equivalent natural gas potential energy would be 100,000 BTUs. So it's 80% efficient, which is not stellar. It's not horrible, but it's, it's not like, wow, that's amazing. Um, if you go look at a furnace, maybe you live in a house where you can see the furnace, you'll notice that they have an input and they have an output. So you can calculate your own efficiency if you want. So this is about 70,000 BTUs in, 57,000 BTUs out. So that's around 81% efficient. And then the furnace down here is 90.5 to 100,000 BTUs, which is around 90.5% efficient. So this one is definitely more efficient. When you're looking at appliances in Canada and the US, we have these EnerGuides, which typically give us an idea of where that appliance sits in the spectrum of efficiencies for all the models in that industry. And so we have here, this is an 83% efficiency rating, and this one is a 98. That's pretty darn good. So those are they're useful to help you understand, what the efficiency is. So I want to spend the rest of the lesson looking at the different types of heating systems. So forced air, hot water, steam, radiant, and passive. So we'll just go through them all. Forced air, which is the cheapest. In your house, you typically have a forced air furnace like this. Apartments sometimes have electric heat pumps, or they have a furnace that's not located near you, or they have a boiler in the basement. So hard to say. But if you live in a townhouse or a house, then you can see how that works down below. Cold air comes in from the house, goes through the furnace, and warm air is blown back out into the rest of the house. And it just goes around and around. In a greenhouse, we don't really have that kind of a context, but what we do is we have these box-like structures called hanging unit heaters, and there's flames inside these aluminum tubes in the middle, and the flames burn, and the gases come off and go out and collect and go out and exhaust outside through a chimney. And these tubes are hot now, and of course there's a fan in the back that blows air through and out the vents into the greenhouse to warm it. You see these in warehouses and maybe sometimes in shopping malls. I don't know, but generally speaking, outside of a greenhouse, you'd see these in a warehouse for keeping it warm in the winter. So that's what a unit heater looks like. So I'm going to do pros and cons for all of these types of systems. So pros for unit heaters are they're low cost. They are dirt cheap. You're looking at about $1,500 to $2,000 for a hanging unit heater of a decent size. And you just hook it up to gas, electricity, and hang it from the ceiling and you're done. Maybe a little bit of chimney work. But if it dies, it's easy to replace. So they're sort of, you can have multiple units and have one turn on, then two turn on, that kind of thing. You don't have to winterize them, right? There's no water in them. So it doesn't mean you have to drain something and make sure there's no water left that could freeze and burst it. They can heat individual sections, right? So if you have a greenhouse with 6 bays, you can have a heater in each bay and run each bay at a separate temperature because they have this sort of different thermostat and each one has its own heater. They are typically inefficient. I think 80% is rare. Typically, they're below 80% efficiency. There is an exception for very high efficiency. I'm going to talk about that in a second. But let's go over the cons. They have a short lifespan, which is not that short, but and you have to keep in mind, hanging unit heaters were designed for warehouses, not greenhouses. And greenhouses have high humidity and extreme temperature fluctuation. So typically where a hanging unit heater might last 20 years in a warehouse, in a greenhouse I think 10 years is about as long as you get before you start having problems. So it's not a huge lifespan. It's not horrible. I mean, it doesn't cost that much to fix them, but they're not going to sit there for, 50, 60 years and last for that long. But nice thing, this should actually be on the other side, I think. There are many, many part suppliers, which means if it breaks, you can easily get a part. Um, One of the downsides is that you're blowing warm air, which of course doesn't want to go down. It wants to stay up. So they are really challenging to get to the crop. So uneven heat is common. Um, they also, because of the way they work, the heat pulses, right? So the thermostat kicks on and your greenhouse warms and then it cools when it turns off and then the thermostat kicks on and it goes up again and then it cools and then it back and forth. So your temperature is just pulsing all the time. And that's not ideal for crops. They like temperatures to be steady. If you want peak efficiency, you don't want to have a risk of, condensation forming on the downside where you get disease. So unit heaters are typically only good for pretty easygoing crops that aren't too picky, or maybe perennial crops in a nursery. They typically use unit heaters in hoop houses. Um, so you don't get that uniform heat that you need for a quality crop. They also dry your crop unevenly because they're blowing, dry, warm air. You know what it's like in the house in the winter when the furnace comes on, your nose gets a bit dry, your house plants suffer, you got to move them away from that vent. We know from last term that warm air holds more moisture, so it has a drying effect. So if you're blowing warm air at your crop, it's going to extract moisture from the crop. And so typically what happens is the section of the crop that's close to the unit heater gets dry, where further from the unit heater is wet, and you end up with uneven irrigation and stunting from the dry cycling at the front, and maybe even disease at the back where it's too wet. They're very challenging to grow with. Just some pictures of what they look like in a greenhouse. Here you can see the fan in the back that blows air through it. Here's your chimney for venting. This is typically what a Modine unit heater looks like. Now, I did mention that they have the potential for high efficiency, and what these are is they're called Holland heaters, mainly because there's one company that makes them. Priva makes a clone, but they burn the natural gas in such a way that it's a very lazy flame, so they can't generate really high heat, but because it would make the machine that big. But each unit here produces a little bit of heat, but it's mostly for producing carbon dioxide. So what they do is a lot of ornamental cut flower growers have these. Instead of having a big CO2 tank outside and running liquid carbon dioxide, they run Holland heaters, which have a flame here, and they move air slowly across, and they blow that warm air out into the greenhouse. And the warm air is high in CO2 because they don't vent it outside. So that means that the burner has to be designed in such a way that they achieve very high efficiency. So there's no chimney, everything is used. One of the nice things is that in addition to carbon dioxide, when you burn natural gas, you get two things, carbon dioxide and water, because it's a hydrocarbon. Just like when your car is idling at a red light, you can see water dripping from the exhaust. That's because water is being produced from burning the gas, which is also a hydrocarbon. So it adds humidity to the greenhouse, which is handy. So not only are you 100%, almost 100% efficient, you're producing CO2 and you're raising the relative humidity. So keep that in mind. I love to ask those questions on the midterm. What benefits do a Holland heater present to a greenhouse? But ultimately, these are mostly used in the ornamental world. And to be honest, I haven't seen many being used in recent years. There was a couple of situations where, and this is also in the older days when greenhouses, you see here this greenhouse isn't very tall. The energy curtain is right above it. And there's a flame kind of that just licks out the opening here, right? And I think insurance companies don't like it because there's a couple of situations where the shade caught on fire. and that shade will spread through the greenhouse like wildfire. And there's been a few fires over the years, so people are a little nervous with them, but they are still around, and they can make excellent backup heaters if you have a failure with your boiler, that kind of thing. Anyways, these links work in your PowerPoint. One of the other things about heating with hot air is that we have different techniques to try to make it more uniform. So remember I mentioned that you get hot, dry near the front and cool air at the back. So oftentimes they have these tubes. These are called convectubes. Now this is really old school here on the left, but it demonstrates it nicely. No one uses anything like this now, but it's blowing warm air into a tube, and then there's holes down the side of the tube. And so what happens is the hot air comes out the holes down the length of the tube, and it's more uniform. These are used in certain circumstances. There's also situations where the blower blows under the bench, and then the hot air goes up to the bench. Here's a picture of one in a really old greenhouse. Look, it's using fiberglass glazing. That's really old. This is probably more common on the right. This would be like a nursery, maybe a tree nursery or a shrub nursery, where they have the tube up at the middle, at the top of the arch, and they blow warm air down, and that air, the entire length of the greenhouse, can come down the side of the greenhouse, and you get more uniform, less hot air blasting on the crop at the front, and you get a uniform heat. It's a great way to have a consistent crop, but it's not perfect. I mean, look at this thing, blocks a lot of light. They get dirty when it's not inflated. They start to hang there. But it depends on what you're growing, right? Like these are probably just growing like little yew seedlings or something. It's okay. There's hundreds of thousands of trees here that are just in the early stages of their crop. They're going to get planted out in a field and be grown on for shrubs. So you'll see these in nurseries a lot. One more time to see a picture of what that looks like. This is just demonstrating the pulsing that you see with unit heaters. So you have this on, off, on, off, on, off, and it's just far less consistent temperature. So looking at boilers, before I get into the types of boilers, I just want to show you the basic layout of a boiler. So here's looking at the external, at the exterior of a boiler, and this is the burner here where the natural gas is combusted. That's the burner here in this picture, this cross section, okay? So in the bottom, let's say half of the boiler, there's a big chamber. There's a big empty chamber where a huge natural gas flame or oil or wood flame is shot into that chamber. Okay, so that's what we call the first pass. And if you look, everything that's blue in this boiler, so down the front, down the back, around all these tubes, everything that's blue is water, and it's all surrounded with water. And so that's what's going to capture the heat from that flame and from the hot exhaust gases and take it out to the greenhouse. So what typically happens is the gas is burnt. We have one pass. It goes to the back of the boiler, hits the wall, deflects up, and goes through these tubes, these little tubes. There's lots of them. And that's what we call a fire tube boiler. Those gases pass through the tubes, come out the other side, go across the front and into the top tubes, and then exit out the chimney, and then exit into the atmosphere. So this is what we call a three-pass boiler. So effectively what's happened is the natural gas has been burnt and gone 1, 2, 3 times through the water before it exits. The more passes we get, the more efficient it becomes, depending on the temperature of the exhaust. But that's basically the anatomy of a boiler, okay? So then that hot water is taken out to the greenhouse, and from the fall, we talked a little bit about this, right? The heating pipes under the benches. We talked about the temperatures that we can run them at, you know, can do passive. We can do radiant by having them really hot, or just convective by being warm. Hopefully you remember that. But in that sense, boilers give us a lot of flexibility because dealing with hot water, we can move it around with pumps and valves and have sections of the greenhouse hot or cool, above or below. Hopefully you remember that stuff. Um, what are the pros? Okay, so we definitely have more uniform heat, right? At the crop level. We have, which basically is kind of the same as better temperature control. They can be more reliable. Modular, I'll talk about that a little later. Boilers are quite expensive, so typically there's just one or two big boilers, but there are situations where you can have many little boilers. Then flexible heat delivery, that is also in the sense that you can have one bay very different or one bench very different than another. So it gives you a lot more control over what to do with that hot water. They have a broad range of efficiencies. I put this on the pro side because, hey, why not? But they typically are 80%. The large boilers are 80%, and most of the boilers you run into in a greenhouse would be about 80% efficient at the boiler. I'll talk about ways that we improve that in greenhouses, but that's later. So cons, they're big and they're expensive. They're expensive to install because you need to build a whole new room for it, a boiler room, and they're expensive to maintain because you need a certified boiler engineer. And because they're sort of expensive and unique, there's fewer part suppliers. So you're dealing with, you can't go down to Canadian Tire and pick up a thermocouple. You got to deal with a specialized industrial supplier. So they're complicated to operate. And that falls into your job description typically as a grower. You have to learn how to operate the boiler and troubleshoot it because most of the alarms that you would get would be on the boiler. And expensive to repair translates back into the first two. And of course, install. You need a separate boiler room. I guess this list is a bit duplicative, but whatever. So what are the different kinds of boilers? So I'm going to go through these, introduce you to them. Atmospheric boilers, high mass, which is two types, fire tube and firebox. We'll talk about modular, and then I'll finish up with condensing boilers. Atmospheric boilers, they're called atmospheric because in the first cross-sectional boiler picture I showed you, the burner had a big blower on it, and that blower not only is to make the flame, but also to push the hot gases through all those tubes. Those tubes create a lot of resistance, which means you need a powerful blower, which uses a fair amount of electricity. Atmospheric boilers, on the other hand, they rely on the fact that when you burn gas, it produces hot gas. Hot gas naturally wants to rise up like a hot air balloon, right? So they burn a flame, the flame produces hot gas, goes up, fills the balloon, and the balloon lifts off the ground. So with an atmospheric boiler, it relies on the atmosphere of hot air rising to go from the flames that are all on the bottom here, producing hot gases. They just rise up over top all the tubes that are in here. So the hot air moves through the tubes and then goes out the chimney. No blower, no real electricity requirements. I mean, you still have to move all the water through the boiler, but you don't have a big blower on this side shooting gases through and up and out a chimney, right? So you might say, well, that's got to be more efficient. But what's the biggest problem? How many times do the flames pass over the tubes? One time, which typically means they are very low efficiency. So they are definitely inefficient. I know of one farmer who has one, and he swears that it's the most efficient thing since ever made, but it's just not the case. The gases are passing once over those tubes, and then they exit out the chimney. And I mean, you can have lots and lots of tubes, and you might collect almost all the heat. That's a possibility. But the issue then is that if you don't have enough heat left in the exhaust gases, they can't get up and out the chimney. And there's a risk that they sort of fall down into the boiler and swirl, which then of course reduces the combustion efficiency because it's like sucking your own exhaust of your car into the intake. It's not going to work very well. So there's just no way around it. These are inefficient. Why would some people use them? They're often used as a backup boiler because they're cheap. So, you know, a standby boiler, or maybe just to produce a little extra heat in really, really cold, windy nights. It's nice that they don't have a lot of electricity. So if you're in a situation where you don't have enough electricity, but you know, I guess a strange scenario. They do react quickly, which is kind of cool. They can produce heat on and off very quickly, unlike a big, heavy, high mass boiler, which takes time to heat and then get the water flowing. You know, these things, it's almost instant heat. So in that sense, they're kind of handy. Um, Typically, high mass boilers come in two pairs. There's an A and a B, a 1 and a 2, and the computer system will run one when it's not too cold and then fire up the second one when it gets colder. And often we'll reverse those roles to make sure both boilers get similar amount of hours on them. They're pretty much always in pairs. And in this case here, there's 1, 2, and 3. Depends on the size of the greenhouse, but typically there's pairs and they just get bigger and bigger. So they're big and slow. They use a fair amount of electricity because of their blower. So here's a blower here, here's a blower here, here's a blower here, here's a blower here. These all have blowers. That's universal. And they're big three-phase motors that use a fair amount of power. These are slow to react. Because there's so much mass, they are difficult to provide decent control in the spring and fall when you have minimal heating demands. That can be a challenge for these. So that's a situation where maybe having a small boiler would be useful for the shoulder seasons when you don't need a lot of heat. Because, you know, heating this giant thing just to put a little bit of heat out in the greenhouse just seems like such a waste. They are typically 80% efficient, which is pretty good, but not stellar. I might as well briefly introduce this unit here. You'll see there's two boilers here, 1, 2, and in the middle is a box. And typically what happens here is the boilers, typically the flame goes through the gas, through the water, and comes out and goes out a chimney, right? A lot of modern greenhouses now have eliminated that. And what they do is the exhaust gases are collected and they go down into another box. And this is called a condenser. And it has another blower in it and a heat exchanger with water. And the blower sucks the exhaust gas because it's now getting cold and it needs help to get blown out the chimney. And it gets blown out this central chimney. And the same with this boiler. Its exhaust comes out and it goes in here and it swirls into this as well. And the idea is that normally in these boilers, the exhaust in the chimney, if this boiler was just venting directly into its own chimney, you would be looking at around 200 to 250 degrees Celsius air. That's a lot of heat that's still in the exhaust gas. And so by putting it through the condenser, we collect that heat into another stream of water and then blow the cold exhaust, which is now around 50 degrees Celsius, out the central chimney. So these condensers are pretty much most greenhouses have them now, because if you combine the heat capture from the condenser with the boilers, you achieve around 98% efficiency. That's pretty darn good. So definitely a worthwhile investment. So again, looking at fire tube boilers, this is just a simple icon showing you the fire tube surrounded by water. This is obviously just one pass, but this is just a diagram to show you how it works. And then the exhaust gas exits, and water circulates around these tubes and gets hotter and hotter, and then is taken out to heat the greenhouse. That's just to give you an idea of what's going on inside the boiler. Where realistically the flame is actually passing through tubes and then exiting out a chimney. And then the tubes are surrounded by water. So they typically once a year, the farmer has to put a brush on a pole down each tube to clean them so there's no dust and debris, which would reduce the heat transfer efficiency. But these are pretty common in greenhouses. Firebox boilers are very primitive. Typically, there's a flame and it is in a giant open area, which then moves up through a few baffles and exits. These are common with biomass, so wood boilers. Wood is usually very cheap, and so we're less concerned about efficiency. And since it's considered renewable, people are a little less concerned about, extracting every efficiency out of it. I think that may be a bit of a poor attitude. In the early days, a lot of the wood furnaces that were being put in greenhouses were very inefficient and actually polluted. Not a big fan of those. Modern ones now are pretty efficient. The wood furnace we had at our greenhouse was around 80% efficient, so basically similar to a regular gas greenhouse. But it was a lot more complicated. And if you want to talk to me about that sometime when we're at the greenhouse, we can talk about it. But I don't want to muddy the waters right now. But yeah, so firebox boilers are typically for biomass, where there's a lot of ash. And you can't have all these tubes, or you need special cleaning systems to keep them clean if you're going to run a wood furnace in a standard kind of boiler, which is what we did at our place. So when you have less tubes, it's less efficient in extracting the heat. So the temperature of the exhaust gas would be somewhere in the order of 200 to 300 degrees Celsius. So there's a lot of heat left in the flue gas, which means it's not very efficient. You're not getting all the heat out of that combustion. Modular boilers. This is sort of a personal little mission of mine. I'll tell you right now, I'm not winning, but this is something I don't understand. If you look at any high-rise building in Toronto or Chicago or wherever, all those big apartment buildings, instead of having big boilers in the basement, they typically have lots of small boilers like these. These are modular boilers, right? So in this case, there's 4 little boilers, but they would have maybe 12 or 16 boilers in the room. And what happens is the computer system starts up one, and if it's not meeting the heat demands, it starts up another one. And if it still needs more, it starts up another one. And so on and so on. And so it can very precisely match the heating loads of the building according to the season. And what's really neat about these is that each of these boilers is inexpensive, and it's just simple connections, gas, electrical. You disconnect it, you can remove that unit and slide another one in less than an hour and have a boiler replaced. So when you have a problem, it's easy to fix. And of course, one of the reasons why they do these in apartments is because if a boiler breaks in an apartment, typically the boiler is put into in the old days with big boilers, they were put into the apartment as the building was being built. And if it dies, there's no way to get it out. You have to chop it up, take the steel out, and you can't build a boiler down there. So they would replace them with these modular boilers. And then as they started building newer buildings, they realized that, hey, why don't we just use these because it's actually better. And I personally think that greenhouses should be using modular boiler systems. There are some out there. Hopefully more will come in the coming years. But these modular boilers can be very efficient. They typically are 80%, but you can also buy 98% efficient ones, what we call condensing boilers. This is an example of 2 condensing boilers that are heating an apartment, a small apartment building. And there's each of these green pumps here is an apartment. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 apartments in this building. And look at the size of those 2 boilers. Like, it's just astonishing how efficient they are. So So the condensing boilers are extremely efficient. In a sense, what they do is they capture all the heat. I have a graph coming up that describes this. Hopefully I don't lose you on this. Bear with me. You may have to sort of rewind and listen to this section a couple times to make sure you understand what's going on. But if you, let's say you're burning natural gas and you have this hot gas is going to the boiler and it comes to the chimney and it's going out the chimney at 200 degrees Celsius. We know there's heat in the exhaust gas still, right? So I talked about how we can divert that hot exhaust gas into a condenser. Think about condensation, right? So in the fall, we talked about how moisture in the greenhouse condenses when it touches the cold glass. So in order for you to get the heat out of the chimney, we need to have a colder surface for that hot gas to touch to collect the remaining heat. And the condenser has to be able to have colder water in it and a colder surface to sort of capture that last bit of heat. And when you get to the point where you actually get all that moisture from burning natural gas to condense and form water, by this graph, you can see there's a huge jump in thermal energy. That big jump takes you from 80% to 98% efficiency. Because of all that moisture that's in the air suddenly going from a gas to a liquid imparts the heat that's in there onto that surface. So we get condensation happening, means that we're getting all the energy out of the flue gas. I've got a diagram here that try to help you understand it. Think of it like this. We know if we put water on our stove, right? And we put heat into it. So we have a flame, we're heating the liquid. As energy goes into the liquid, eventually it starts to vaporize and form steam, right? So we know that in order to go from liquid to steam, we had to add energy. Which means, if you think about it the other way around, if we're able to take the steam from the boiler, right, and condense it back to a liquid, it gives up the heat that we added to make steam. And if you think about it like that, think of how much heat you put into a pot. It gets pretty hot before it starts to steam. And if you can actually take that steam and reverse it to a liquid, the same amount of heat that went in comes out. And that's how you go from 80% to 98% efficient. A lot of modern homes now use condensing furnaces. And they're so efficient that they don't even need a metal exhaust. They just use plastic because all the heat is captured because it's condensed. And that gets all the heat out of the exhaust so that it's fairly dry and cool. So that's how condensing boilers work. Before I continue on with steam boilers, I will mention there's one caveat. We'll talk again about this, but one of the challenges with condensing boilers is that you have to have cold enough water to cool the chimney down to get it to condense. And typically we run our heating pipes in the greenhouse at around 50 degrees Celsius. And unfortunately, 50 degrees Celsius isn't cold enough to get the moisture to condense. Think about it, 50 is pretty hot. Your average summer day is maybe 30 degrees Celsius, and there's nothing condensing on you. You're trying to evaporate, to sweat. So when you run a condensing boiler in a greenhouse, typically you have to have different zones or circuits that you can run very cold. And you use those circuits to collect the remaining heat from the boiler. So for example, if you have a packing area where you're not growing crops and you want to keep it at 10 degrees Celsius, or a loading dock area where the trucks back up, you can heat those zones off your condenser because the water is cold and will be cold enough to allow it to condense. So it takes some thinking and some design to be able to run a condensing boiler in a greenhouse. When condensing boilers first came out for greenhouses, a lot of farmers were being sold on them because they're 98% efficient, and they would install a condensing boiler in their greenhouse, but the hot water loop was never colder than 50 degrees Celsius, and the thing never condensed, and so it never operated higher than 80% efficiency. And they were started getting really upset. And of course, salespeople will sell you whatever, right? They don't always even understand what they're selling. And as it turned out, they had spent all this money ripping out their boilers, putting in this new boiler, and in fact were burning the same amount of gas and didn't save any money whatsoever. So they had to redesign their heating system to make it so that it would condense, and then they capitalized on some of their investment. Going on about steam now. So steam boilers, you typically only run into these in cut flower operations. I think Jeffrey's Greenhouse is the only one I know of that is a potted plant producer that uses steam in one of their farms. But cut flower growers use them all the time. Steam boilers are dangerous because you can have potentially very high pressure. They require a lot of maintenance because you're bringing air into the boiler all the time, so you have to add chemicals to prevent corrosion. You have to add water regularly because you're creating steam, which means you're losing water out of the system and steam, so you have to add it constantly. But cut flower growers use them primarily because they take the steam out and they put it under these heavy mats, and they'll put weights down the side, usually chain weights, and then they put steam under this mat for a few hours, and the steam will superheat the soil down to about 2 feet below the surface, and it kills all the pathogens that exist that would potentially insects, bacteria, fungi, everything gets killed that would potentially infect their cut flowers. Now, I know a lot of you are saying, but wait a minute, there's beneficial bacteria and fungi, and you're 100% correct. But it's cut flower operators, man. That's what they do. They traditionally, if they don't steam, the biggest issue is weeds. If you've ever worked on an organic farm where herbicides are not used, they usually use mechanical tilling. You spend 90% of your time pulling weeds, trying to keep your crops from being overrun by weeds. And cut flower operators just can't afford to have weeds because weeds attract insects like thrips and aphids and mites, and weeds use the nutrients, so their flowers end up being smaller and uneven. So by steaming, they keep the weeds under control, they keep the pathogens under control. But my neighbor at our farm was a cut flower grower, and he steamed all the time. And he was fairly conscientious about the soil, so he would actually irrigate in bacterial and mycorrhizal inoculants after he steamed a bed. And they would steam each bed maybe 3 times a year, so they had to restart the bacteria 3 times a year. But it's only 2 feet down, and there's stuff below that will migrate back up into the area. But the weed seeds are killed on the surface. So, anyways, that's steam. Steam boilers, they look just like a regular boiler, except that they drain the water down from the top. They leave an airspace, and that allows steam to form, which then they collect and send off. It runs higher temperatures like steam. If you've ever burnt your finger on a kettle, steam is way hotter than hot water. Remember, water, the hottest water can get is 100 degrees Celsius. The second it turns into steam, you can achieve very high temperatures, 500 degrees Celsius. That's a huge difference compared to water. So there's definitely a lot of energy, potential energy in the steam. They do react fairly quickly because when you produce steam, it shoots down the pipes into the greenhouse and then hits the heating pipes, and they get very hot and they radiate that heat in all directions very quickly. And then it sort of condenses as it cools, and then it drains back to the boiler. So they do react quickly, but they do require a lot of maintenance. I'll let you read this when you're looking at your PowerPoints, but this was in San Antonio in 1912. There was a train steam engine that blew up, and just absolutely devastating. Like, the amount of energy that's in a boiler is unbelievable. In all my years, I never saw it, but I've only heard of one steam boiler that blew up in a greenhouse, and The end shot off the boiler and went into the parking lot and wrecked 4 cars. I think they got off lucky. Could have been far, far worse. But generally speaking, the government has been sort of cogitating to stop the use of steam in greenhouses unless the greenhouse hires a boiler engineer. Well, they're expensive. So I think more and more cut flower growers are buying what they call steam generators, which are run off electricity or natural gas, and they're not really a boiler. It's like a big kettle that makes steam and on demand. This is, if you're interested in Mythbusters, they did a little recreation of a hot water tank heater blowing up, and it kind of demonstrates pretty well how much energy is in steam. So if you ever end up in a greenhouse that has steam, just make sure you are careful, pay attention. This is the condenser I was talking about. So sometimes they're called flue gas condensers, or they're nicknamed economizers. That's where I was talking about recovering latent heat, right? When you're taking the hot, moist exhaust gas from the boiler and you divert it down into this other heat exchanger, capture the latent heat, and then vent it out. They are phenomenal. And one of the secondary benefits from these is that the flue gas is cooled down and all the moisture is removed enough that you can actually take the flue gas and you can collect it as CO2 and put it into the greenhouse. And that's what the veggie industry guys do. A lot of ornamental farmers are doing that as well now. So they're fertilizing their crops with carbon dioxide directly from their boilers because they're running it through their flue gas condenser to cool it and capture the moisture so that they're not pumping steam into their, moist exhaust gas in their greenhouse. That would just be full of disease in no time, right? So it's dried in the condenser, captures the heat, and then CO2 goes into the greenhouse. That's super efficient. That means that not only are you collecting 98% of the heat, but you're also collecting the carbon dioxide so the plants can actually feed off of it. I'm not going to go over this again because we talked about it last term. So remember the difference in terms of, radiant heat. In terms of radiant heat with gas, typically greenhouses have sort of a long tube that has a flame in it. You see them at hockey rinks sometimes for heating the grandstands. They're not really well suited for growing crops. They're more, if you see them, they might be at a garden center where they're sort of just temporarily heating a crop for the couple of weeks that it's sitting there waiting for you to buy it. They look like this. There's a burner on one end, and there's a long tube with a little flame all the way along the entire tube. And inside that tube, it heats a bigger tube, which gets radiantly hot. And then the reflector that's around it, so think of it like this. There's a big tube, and inside is a flame tube. And then there's a reflector on the outside. And this flame tube gets this tube so hot that it radiates heat in 360-degree directions. And of course, the heat that's radiating up, we don't want to lose it. So it hits the reflector and bounces back down to the crop below. So these radiant heaters are used, sometimes there's ones like this too. These are catalytic burners that just radiate heat directly, and then the side reflectors kind of focus it. Again, not really used in greenhouses per se, but I have seen them used in garden centers. We see these in greenhouses in packing areas, in loading dock areas, where they're trying to keep staff warm in one area but not heat the whole thing because it's a big area. Some greenhouse packing barns are massive, right? And to heat the whole thing to 20 degrees Celsius just doesn't make sense. So they'll heat the area where people are working. Here's just a couple of examples showing radiant heat in the ceiling. Not only are they, a pain to work with, but look, they block light. So typically garden centers would use these. You wouldn't see these in a production facility. Or you see them in restaurants. Like you've probably been near one of these where they radiate heat down to all the tables that are sitting nearby. Then there's a different kind of radiant heat, which is related to our hot water, and that's in-floor radiant heat, where all the pipes just crisscross through the concrete in the greenhouse, and then the whole concrete gets warm and radiates gentle heat up. Um, a lot of ornamental greenhouses do this, not veggie farms, but the ornamental guys, because when it's poured nice and flat, you have this huge uniform smooth surface. You can drive forklifts everywhere, you can roll carts everywhere, you can flood irrigate and drain. Uh, just a ton of flexibility with what you can do with it. You can also run radiant heat right on the benches. These are black tube mats that get heated directly at the root level. So haven't seen that too many times, but there are some crops that will do this. A lot of times when you have really cold air and really warm roots, you have some serious physiological problems. So, but for rooting, it's good, but that's it. I wouldn't produce on that. This is just a picture of biomass heat. You can see how much space it takes, specialized space. You know, you got to store all your wood, and then you need your boiler room, which becomes a much bigger boiler room. Yeah, they are typically 60% efficient. That's pretty bad, I will admit. I think ours was close to 80, but not quite 80. But yeah, we had a big barn just to house the whole thing, and then you have to have trucks to haul the wood, and it's a big investment. And it didn't work out for me probably because when I bought it, the 2 years after I installed it, the price of gas went below 20 cents. So I was saving 5 cents a cubic meter. It wasn't enough. But, you know, what do you know, right? It's so hard to know what the future holds. We do our best. And I wasn't the only person that went into that, so didn't feel like an absolute idiot. Um, and typically you do need one employee to run the entire thing. They're so complicated. You need a dedicated person. So that you have to be big enough to be able to afford that, right? It's not going to be just mom and pa. Other alternatives, biogas. This is pretty cool. We actually have one in the Niagara area, two in the Niagara area, one in Virgil and one in Jordan. If you see these silos with a green dome or some sort of dome structure on top, those are anaerobic digesters. And so what they typically do is biological waste is put inside and fermented. And when you ferment biological waste, it produces methane. And if you remember from the beginning of this lesson, methane is mostly what natural gas is. So basically what happens is the farm produces its own natural gas from these units, feeds them into a boiler to generate heat. Or better yet, they feed them into a big engine, which runs, this is the engine on this side, which runs a generator to make electricity. And the water that cools the engine goes out and heats the greenhouse. And the exhaust, once it exits here, is CO2. So we keep upping the efficiency here, right? So just think about it. If you have biogas and you're producing your own electricity and you're collecting your own CO2 as a fertilizer, how much more efficient can you get? There's a couple of farms in Leamington, Great Northern Hydroponics is one, that these generators are so big that they provide excess hydro that feeds into the Ontario grid and provides enough electricity for like 100 homes, a couple hundred homes. Anyway, so yeah, biogas or anaerobic digesters are important. Why is it anaerobic? If you remember, we have both aerobic composting and we have anaerobic composting. When it's anaerobic, we get methane. When it's aerobic, what do we get? CO2. CO2 is no good to us unless we're feeding our crop, which is fine. That's where those those mushroom bags that produce CO2 from the composting of the mushrooms feeding on the substrate. Some of the cannabis guys will know about those. That's aerobic digestion. Anaerobic produces methane. So the methane has to be burnt as a fuel. This slide is just out of interest. You don't have to memorize this, but basically what it's trying to say is that in North America, we produce our electricity from coal and natural gas, other fuels, and nuclear, and then renewable, maybe hydroelectric stuff like that, water dams. But if you look at this, coal and natural gas and other petroleum, which is maybe in the northern communities, they're burning something to make electricity, and almost 64% is lost as heat, was just wasted energy from that whole process. So this graph just demonstrates how much is lost in heat. This is making a case for what we call combined heat and power. So if we can use the heat, right? Something efficient, use that heat. So let's say you have a natural gas fire, say here in Ontario, we've got Nanticoke that produces electricity for Southern Ontario in combination with Bruce Nuclear and Darlington. That's where we get most of our electricity. So about half of our electricity comes from Nanticoke natural gas plant. What if we took the heat, look at that wasted heat, and had some greenhouses near there? And we use the heat to heat our greenhouses and not waste the heat, but use it to grow food. That's the kind of thing that I think, we should be looking more forward into the future with. Geothermal, I'll quickly describe that. This is where, if I can think about it like this, if you ever go to your kitchen and you have your fridge, if you've ever looked at the back of the fridge or felt the back or the side of the fridge, it's hot. Sometimes there's a coil on the back, sometimes it's actually built in, it's just a smooth surface, but if you put your hand back there, it's warm. And you may wonder, why is that warm when this is a fridge that's getting cold? And that's because it's using a heat pump. And so that pump effectively is a pump that's taking a chemical, Freon or whatever, and it's converting it from a liquid to a gas, and then letting it condense back into a liquid. And of course, remember we talked about latent heat. So when you go from steam to a liquid, it gives up the heat that was put in to make it steam. So it's effectively in a fridge, just like the air conditioning in your car, that compressor compresses the gas so that it gives up its heat outside the fridge, and then allows the gas to come into the fridge and condense around it, absorbing the heat from the fridge, which cools the fridge. And then what you can do with these heat pumps, which is pretty cool, is you can actually reverse the flow and do it the other way. So you can actually heat the fridge and cool the outside if you reverse the pump. And so with geothermal, that's how it works. You have a giant refrigerator pump, and it will heat a liquid and either have that heated liquid in the greenhouse to heat it in the winter, and then draw the heat from the ground by having the gases down there, or it reverses and it can cool the greenhouse and heat the ground during the summer by taking the heat from the greenhouse and storing it in the ground. So geothermal is pretty cool. It still uses electricity though. So then you have to ask yourself, where's the electricity come from, right? So if you're using electricity that's generated from Nanticoke, well, you're looking at 60 to 80% efficiency in the combustion of those fuels. Or if you're getting your electricity from a nuclear plant, now you're using producing nuclear waste for your geothermal. So geothermal is a tricky one. People like it because it's technical and cool, and it can be very efficient. But you do have to ask yourself the question, where is my electricity coming from? We'll talk more about that system. Lastly, and most interesting, I think, if you're the organic farmer type, I think these are really cool greenhouses. This one looks cool. It's maybe not the best design. I got a couple other slides coming up. But passive solar, effectively the way it works is you have a south-facing greenhouse. Because primarily, let's be honest, an organic farm, they're only going to use their greenhouse to start their plants to get a good start on the growing season. So they're heating their greenhouse in early spring through to June. By then they've got most of their stuff done. They may not have a greenhouse going year round. It's possible, but they get very hot and crops tend to not do very well in them once you get into the summer. So the issue is, how do you keep your seedlings from freezing, right? Are you going to heat it? And a lot of organic farmers are trying to find alternative and more sustainable ways to grow. And so some of them have turned to these passive solar greenhouses. And the way it works is that when the sun is shining, it heats the greenhouse, which is fine. That's great, right? You've got your crop sitting on a bench inside here growing, leafy greens and maybe seedlings. And as the greenhouse is being warmed, it warms this northern wall. Now the northern wall, because it's in the spring, the sun is so low in the sky, there's no light on this side. The sun is maybe maximum declination, 30% or 40 degrees up. So the back can be insulated and have a thick sand or straw bale mass. The idea is you have to have a lot of mass, and it warms up. And then when the sun goes down, man, this looks like a mess. I got lines going everywhere. When the sun goes down, it's nighttime, this mass will slowly radiate heat out and keep the greenhouse above zero. So that's a passive thermal mass greenhouse. It has to be well designed. Like this is sandbags that are I think is 1 layer, 2 layers thick. I'll be honest, that's not even nearly enough. This guy's made a beautiful greenhouse that's not going to work. Here is a picture of one that will work. Look how massive this is. This is sand, and they've got straw bales on the outside and then sand, and then they've covered it with a concrete parge so it doesn't rot. And during the day, the greenhouse is warm, and this warms up, and at night, it all radiates warmth out into the greenhouse to keep it warm. And even more efficient, this is one being constructed at a farm in Saskatchewan. In addition to the north wall being thermal mass, they also have solar paneled fans that suck air from inside the greenhouse during the day, and the air gets blown down into these tubes. These are collectors, and if you'll notice, there's tubes in the gravel. They come across to a collector on the other side, and the idea is that the air is blown down into the ground, goes across, comes out the other side, up the other side. And this will all be full of gravel. So the entire bottom of the greenhouse becomes a giant thermal mass. And as the warm air during the day passes through, it warms the gravel. And then the solar panels that are operating this also charge batteries. And then at night, the fans on battery power will continue to run, and they'll take the cold air from the greenhouse, blow it down to the ground. The warm gravel warms it, and warmer air comes out the other side. And the process repeats itself every day. Passive greenhouses work really, really well in Saskatchewan and Manitoba and Alberta. Anyone know why? Maybe because they have way more sunshine in the winter. One of the big problems we have in Ontario with passive solar greenhouses is that unfortunately we just don't have enough sunshine. Down in the Leamington area, there's more sunshine in the winter, so this could possibly work. And it's milder, you're less likely to freeze. So I could see this working in that context, but maybe not on a large 35-acre scale. But for an organic farm, perfect. But a lot of Ontario just doesn't get enough sunshine. And people who have tried this, they get enough latent heat, or stored heat in the mass for maybe 1 or 2 days, and then they fall behind, and there's just not enough heat in the system, and they have to turn on a gas burner to keep things from freezing. So other simpler things you can do if you have a hoop house, say you just want to cut down on costs, black barrels full of water, put them underneath all your benches to support the benches, and the barrels will store heat and radiate at night. Even if you're not building a thermal mass greenhouse, it's a good idea because it will still contribute to heat. This is actually a diagram from an old greenhouse book from the 60s when they did a lot of research on this stuff. And a lot of this isn't new, right? It was done before. And they have big, thick insulated curtains that they drop at night over the glass, and they've got barrels of water to form thermal mass so that it doesn't freeze at night. You just have to open and close this curtain yourself every day. Could work. Anyways, all right, that's my rather lengthy introduction to heating systems. Sorry that was so long. That's 1 hour and 15 minutes or something. Wow. All right. I'll hopefully see you guys soon. Take care. Bye.